All right, so we've got the, we're just going to load some stuff in the program counter, and then we're going to go down here and we're going to jump to a label. Now, the key thing you want to look at here is what's going to happen here. The machine code, now how does it know where to jump to? Here's the label down here, all right? So when I jump to this LBL underscore name, it's going to bypass this piece of code and then run this, all right? The question is, when I look at the opcode for this, 940C is a jump, but it's got the 0006, okay? It's got to figure out where to jump to. Where is this label name? And if you notice, the physical address in flash program memory for where you're jumping to is what? 0006. That's sitting right there, all right? Now, how many bits is a jump instruction take? How many bits? 32 bits. 32-bit. Because look at it. How many bits is this? Well, 9 is 4, 8, 16. There are 32 bits. All right? That's why we have something called a relative jump. That'll only, see here, what I'm allowing you to do is I'm giving 16-bit addressing on the entire flash memory. Okay? This is the address of where I'm going to go to. It's 16 bits. If I have a very small, tiny amount of flash memory, you can use what's called a relative jump, which only allows me to jump within, I think it's plus or minus 2K. All right? So it allows me to jump around in like 8K of addressing, or 4K of addressing space. So that's the key here. Now, if you notice down here, we jump to the label name again. Here's the opcode, 940C. All right? Notice the address of where I'm going to. 0006. Tyler. It would never even run that code. No. It's just an example. That's all I'm trying to illustrate here. So what happens is the 006 goes up to the program counter. The program counter immediately goes down to the address 006 and starts executing that code. All right? It executes it. It now jumps back to that label name. Notice that the program counter was incremented to 7 because it did the add here. All right? And now it's going to take that 006, goes back up, and now it starts executing that code. And effectively what you're going to have here is just an infinite loop. It's just going to keep doing this forever and ever. But the idea here is I wanted to illustrate to you what is happening with the program counter and this physical address for where I'm going in Flash. Rachel?
So if we wanted to exit the loop and just jump up to that LDI R18, for example, because like it's there, like you would.
Yeah, you would have added another label here.
Oh, okay.
Just add another label right there. All right, and then you could have jumped to like LBL name 1 and have LBL name 1 up here with a colon after it.
Why would we want to skip those 2 lines?
It's only I'm only trying to demonstrate what is happening with the program counter and what's happening with the address. That's all. Now, I mean, yeah, it would make no sense to this will never get executed. Yeah, and here I'm just going to have an infinite loop here. But the idea here is what's happening with this and this, as far as where they're going. Okay, good question. No problem. All right. The I jump is an indirect jump. Why do we call it an indirect jump? Because where is the address that we're going to go to stored at? Z register. Anytime you're dealing with the Z register, that's physically going to contain the address of where I'm going to. All right? It has no operand. The program counter is loaded with the contents of the Z register, and Z points to location. What's that? What's the matter? Okay. I met your drill instructor today. The bald-headed Oriental guy. I said, you know this guy Amigon? He says, yeah, the Egyptian dude. Yeah, you're in the National Guard too? Yeah, good for you. All right, thank you for serving. All right, so the I jump is basically the most significant bits are loaded up with 0 because here we're just going to have the Z register gets loaded right into those 16 bits for where the program counter is going to go. Okay? So it's a 2-byte instruction. It's just a 16 bits on where I'm going to jump to. So the Z register will just, whatever the contents of the Z register are, they go right into the program counter. Now the question is, I'm doing 16-bit addressing here. If I have a lot of flash memory where maybe I'm using 22 bits of addressing, just in case you have a really huge amount of flash, the Z register may not be able to access all that flash space. So then you use what's called the extended Z register, was the ramp. Remember, I don't know if you remember, there was a ramp X, a ramp Y, and a ramp Z. Those you can extend out to 22 bits. But we're not going to worry about it. Everything we're going to deal with is 16-bit. Just to let you know that you may want to go to. All right. So it's all it is. It's just pointed by what's happening in the Z register. All right. So you can just basically now relative jumping. This is where we're going to have the new program counter will equal the old program counter plus some operand here. Okay. And what this allows us to do, relative jump, instead of the JMP, it's RJMP. It allows me to jump inside of flash wherever my program counter currently is. It allows me to go backwards 2048 address or forwards to 2047. Okay. All right. So that's basically what you got here. All right. It's giving me the address space right here is going to go from minus 2048 is less than n, which is 2047. All right. You don't have to worry about these numbers. Well, you will. I mean, it depending upon where you're jumping to. But usually you just give it a name. All right. It's a 2-byte, 16-bit instruction. The first 4 bits are the opcode, and the rest 12 bits is the relative address of the target location. So the relative range goes from, again, we're dealing with 12 bits, so I'm going from 000 to FFF, and it's divided into a forward and backward jumps. I can jump backwards or up in my code, or I can jump down in my code. All right? So therefore, the minus 2048 and the plus 2047 words of relative memory to that address of the program counter. All right? It's done by looking at the 2's complement. If I take the 2's complement of minus 2048, it's 800, and 2047 is this, 7FF, divine intervention. Somebody's knocking up there. All right. The jump is forward, the relative address is positive. You're going to be jumping down in the code. If the jump is backwards, all right. If it's backward, then the relative address is negative because you're going backwards. Okay. And it's the 2-byte instructions refer. It's preferred to the JMP. It's just really when you're coming down to really fighting it out with program memory and the bytes that you actually have. This has two whole bytes less. Woo-hoo! All right, you save 2 bytes. All right. So again, what you got here is wherever my program counter is, I can jump back 2048 or forward to 2047. Okay. Okay, all right, so the relative jump. Here, watch what happens with the program. All right, so we're just going to load up a 15 into our 16. A 5 goes into our 17. Now we're going to jump down to this label name here. All right, so now what we're going to do is we're going to take the program counter plus the offset. Okay, so what we have here is the 2 comes up. You add it to the 3. That gives me the 5. The 5 now goes into the program counter, and now I jump down to the label name. Okay, so it's the program counter plus the operand is going to be my new program counter. Let's look at that again. So here I have the machine code for this RJump label name has a 002 here. All right, the opcode for it is a C. All right, down here here. Are we jumping down in the code or backwards when I'm up here? I'm jumping down. So the offset address is going to be a positive number because we're going this way. Now, if you look at it, when we go back here, when I'm down here and I'm jumping up, what's going to be the opcode is going to be positive or negative? It's got to be negative, and you can see it right there. It's 2's complement, all right? That's stored in 2's complement. So, all right, so we come chugging down. We hit, here we go. We're now going to jump to the label. Watch the program counter and watch the offset. Now we're going from uno, dos, tres. All right, so we're making 3 to get from there because as soon as this is executed, the program counter is going to go to 3. So watch this guy. 3, the O2 comes up, which is the offset. Adding it gives me 5, which is the physical address of where I'm jumping to. Blackboard magic. All right. So now we're jumping down to here. We execute the add, and now I'm going to jump back. So now the machine code for this is FFE. There it comes up. Adding it. When you add those together, it's 5. It's 5, and then now it goes back up. All right. So let's look at that again. Here's the add. Watch the program counter is going to go 5. Now it goes to 6. Now it's going to, when it executes this, it goes to 7. So this will change to a 7. This FFE comes up. When you do that addition, what's 7 and E? Add 7 and E together, what are you going to get? No, you're going to get 5. You get the... You're all looking at me a little glazed. Must have been a great Eagles win yesterday. A little pate time. And what's E? FFE. Okay. And we got the 7 is what? This, right? 1 and 0. 1 and 1. 1 and 1. Oh, wait, 1 and 1 with a carry, right? All right. You're going to get, all the ones are going to be flushed out here. I'm going to be left with all zeros here. And what's that number? What's that? That's the 5, and that's where we're going to. All right. That's brought in. It's just it takes care of the 2's complement. All right. Whatever that number is there, it's copied. If we go back, watch what happens when we come forward. Again, this is how many bits in here, Michael? How many bits? How many bits? 12. And how many do I need to address flash? 16. Unless I got big flash, which is I need 22. But right now we're going to be working with 16. All right? So watch what happens when we come down here. You will notice that this is 12 bits, but I need 16 bits. A 0 will pop out of this thing. It just copies it. All right? So notice the 0. Watch another 0 come flying up. That gives me the 16 bits that I add to, because the program counter is 16 bits. So I have to add another 6. I mean, I've got 16 bits, and I'm adding 12 bits. I got to add the other. It just copies whatever's the 12 bit, you know, the 12 bits. 9, 10, 11, 12 get copied, and then just tacked on. French, right? Vive la France. All right, vive la France. Pepe Le Pew, all right? Wee-wee. So now we come down. If you notice here, another F comes up. It copies it. Now we add those 2 numbers together, just like we did here, and we get a 5, which is the relative address of this guy right here. So again, and I put those on the slides to give you what's happening there, okay? This is just a quick example, too. Jumping to 2 different places. It's going to compare something. It's going to branch on a not equal to 0. It's going to look at the 0 flag. If there's an error, it jumps here. If not, it bops down here and it jumps to OK. Just some examples of relative jumping. All right. This is all it's jumping to a label name. That's where it's going. All right. Now we can start in Fortran. You guys never. Anybody heard of Fortran? A couple of hands. I used to hack that. Fortran was my big thing. In C, you have for loops, right? And you have while loops. we have to generate them in assembly also. So in order to do that, we need to set up counters and we need to test conditions. Like you have for I equals 1 to 100, I plus plus, right? That's going to set me into a loop for 100 times. It's going to do it no matter what. You can have while loops while you're testing some condition. We're going to have the same thing here. Yeah? Oh, don't you love it, huh? The melodious. All right, so what you've got here is the branch equal. I mean, I just listed them all for you. All right, they're there. You don't have to memorize this stuff. You look it up. All right, for all the branching. Okay, you can branch on a half carry. They give you all of these opportunities to branch based upon what's happening in the actual machine itself. All right, branch on same or higher, branch on carry clears, branch if lower, branch if carry sets, branch if not equal. So we can do now. The idea for this is to do two things. You can set up conditions on which I want to loop on. So I'm testing something. I could be grabbing bits in off an I/O port, testing them, and then that could give me some kind of condition of which to jump to. I have port D is tied to 8 windows or 8 doors on a floor in a building or something. One of those bits starts going high or low on me. I can test that condition and set off an alarm or something. All right. And loops are just brute force. You're just going to loop it. All right. All right. If I'm going to go through an array of data that's 50 RAM memory locations, bam, I'm going to run right through it. All right. Yeah. Relative jump. Yeah, indirect. Yeah, that's just using, again, that's R jump. I'm sorry. Let me get back here. I jump.
Yeah. You said that if we have a really big flash,
yeah. The Z register has what's called a ramp Z associated with it.
So
it makes it 22 bits. And it, okay, hold time. If I've got a really large amount of flash, okay, 4 meg, all right, big time, all right, I can't address that with 16 bits. I now have to go to 22-bit addressing. The Z register does not hold, it only holds 16 bits. There's something called the ramp Z. If you look in my chapter 2 slides, you'll see I mentioned this ramp Z, PZ. Yeah, and that takes the X register and it also adds on another register that gives me the other 8 bits of addressing.
What register is this one? Is it located in those
The R30, I forget where it's located. If we can jump back to the chapter 2 stuff and it'll be in there. All right. I just want to kind of get through this jumping around on a Monday. All right, so we're good here. Good here. All right, software development. All right. It's amazing the emails that are going around in the department about students can't code. You guys had MATLAB, right? Can you feel comfortable writing MATLAB code? No? Some no, some yes? All right, well, guess what? I mean, whatever they say, and whoever they are, I won't mention, but here you will write code, all right? Here you will write code. And it's important that you're doing software development stuff. Now, we're not going to the examples in the book are nice. They're short, 15 lines of code, something like that. When we get to running a DC motor and using an interrupt with an optical sensor on it, this code's going to start getting long. You need to develop good skills in how do I write large pieces of code. You just don't sit down and start hacking code. It's so inefficient. You've got to set it up in your mind on how am I going to develop this stuff. All right? It's key when if you're doing little short stuff, you can get away with it, But you've got to develop, when you're developing algorithms for problem solving and reusable software, you've got to be able, I run into this all the time with my Rocksat group and with my Lunabot group because we're literally writing tens of thousands of lines of code. And now if somebody's going to come over and take it for next year, you've got to have that code organized and documented well, because the person who wrote it's no longer here. Somebody else this year is going to pick that code up and have the robot run in this arena. And there's literally, it's got to be documented. So the idea here is that you want to have useful tools for debugging. Is the nice thing is we have Atmel Studio 6, and we have the, you're going to get your little, well, you already had the programmer, right? Everybody's got their JTAG? Well, that's a great tool for debugging. It's an in-circuit emulator. I can go down to the butterfly board as it's running and see every bit and all my registers and everything, what's going on. It's a beautiful way to debug things. So we're going to get used to these tools. Good programming style is key. Yeah, flow charting. All right, so you flow chart. What's the flow of the program going to be? Typically, this is a start or stop. A box is an operation. Little rhombus here is an input or output. This guy is a decision making, usually to some connector or out, and then you have some program, could be some subroutine or subprogram down here. All right, so it's important for getting a good style. All right, so now, if we're going to just write a program that says, all right, if R26 is less than R24, then R22 increases. All right, so if we look at it, if R26 is less than R24, there's the test. If this is false, nothing happens. You bail out. If this is true, we increment R22. This may seem like a trivial example, but you have to get these concepts down. So if I'm going to test. If R26 is less than R24, I'm going to branch on a carry clear to L1, which is going to bail out. All right, so in that case, it's not. I'm bailing around here. If it is true, and this is where I have to test it, the actual testing is done in here with doing a subtraction and then using one of my conditional operators, okay? Branch on carry clear, branch on carry set, whatever. Now here we can do an if-else construct. In C, if I want to, let's say R17 set to 5, if R20 is greater than R21, I'm going to increment R22 once. Else, if this is false, then I'm going to do a decrement, and then I'm going to increment R17, just as an example. So here I set up R17 is going to be 5. I do the testing here. Is R20 greater than R21? No. Increment R22 and increment R17. If it's a yes, I'm going to increment R22 and increment R17. All right, so if I load this in assembly, I load in the 5, subtract R20 from R21, branch on a carry set to an if label, which is right here. Increment R22, increment R27. If the branch on carry set is false, if it's true, I'm going to decrement R22, then jump down to the next and increment R17. So this is a C construct, and this is the assembly, okay? Here, if I want to set up a loop, all right, if I'm going to add R30 to R30 and R31 9 times, I have to set up again. I'm going to set up any one of my general purpose registers, 16 through 31, to set them up to be a counter. All right? Add the numbers together. I can decrement it, and then I'm going to test. Is R16 greater than 0? Yes. I keep going back and I keep doing this. If no, I just fall out. All right? All right, so now I'm going to calculate, I'm going to add 20 down to number 1. All right? So again, we're going to set up a counter. I'm going to have R17 is going to accumulate a result here. And I'm going to add R16 to R17, decrement R16, test if it's greater than 0, bop back up. Keep doing this until I get down till R16 hits 0, and then I bail out. Okay? Oops. Oh, with this thing. And that's the code for it, okay? Org is just a compiler directive that says, okay, I'm gonna organize everything at program at locations address 00 in Flash. We'll be playing around with this a little bit later, but here we load up R16 with the number 20. R17 is where our results are going to be accumulating at, okay? I add R16, R17, so that gives me 1 plus 0, all right? So I add them together. Decrement R16 goes from 20 to 19, branch not equal. If that was that result 0 result, no. Branch on not equal back here. And just keep chugging in there until I get done. All right, we also have a loop for, again, for those who have had C, and a init condition, and then a calculation that can go on, and then just do something inside your little famous squiggly brackets there, okay? So again, initialize, do something, do a calculation, test a condition, go back if the condition is true, bail out if the condition is false, and then you're done. Okay. All right. So here we're adding all odd integers up to 27. So again, I'm going to set up R20. I'm going to make R16 1, and then I'm going to start adding up. R16 will equal R16 plus 2. So I'm going to go 1, 3, 5, 7. And now I'm going to test if R16 is less than the number 27. All right? Because that's the final number I'm going up to. And again, so we load up a 0, load a 1 in R16, add them together, load R17 with a 2, add them together, load R17 with a 27, subtract, branch on a carry clear. All right? Branch on a carry clear back to here. If the carry is set, we bail out. We are done. And it's just, I ran the code for you so you can just see when it finally got down to 27, the carry flag was set and we were done at that point. All right? Yeah?
Why do we have to load 27 into R17 every time? Like, can that be put above the loop? Because R17 can just constantly be... Oh, because you're adding them.
You're adding them.
Okay.
Yeah, you're adding them together. All right. So that's basically how we do in branching. Now we're going to get into how do we generate time delays. Time delays are useful for when you're doing pulse width modulation. If I want to have, I set a port pin B 3 high, I got an ultrasonic sensor or a servo motor attached. I got to do a 1.3 millisecond pulse out there to force it to go backwards. And then I need a 20 millisecond delay between the pulses. If you've worked with, how many have had intro to engineering? Right? You've seen this stuff. I mean, we did pulse width modulation there whether you knew it or not. So now we have to generate different lengths of pulse widths using time delays. The real way to do this, and most of the time you're going to do this is using what's called a counter. All right? Counters are great. But we're going to show you how to generate a time delay. Time delay ties up the processor. The processor has nothing else to do but sit here and just wait, doing no ops or whatever. When you're doing a counter, the counter's off doing something and you're doing something else. So it frees up your program not to be sitting there just waiting for stuff. But we'll get to that, okay? So now what we're going to do is you look at, there's a little crystal that sits out there, and that sets the speed at which the processor is going to run. On the ATmega, it's all in pins 12 and 13. I'll have to look on the butterfly board. It's there. I forget exactly what pins. Now, the Mega 32 is a DIP, all right? It's a dual inline package. The butterfly board is a quad flat package, all right? So they're just manufactured a little different, all right? Time delays. What we're looking at is here is where you have to know two things. How many machine cycles does it take for an instruction to get done, and how fast is my machine running? So if you look back in Appendix A, you will see for any of the loads and any of the adds, this is one of the key features of this Harvard architecture. Everything's done in one machine cycle. We will see that when we have conditional branches, you pay what's called a branch penalty because you have to test that condition. All right? And I'll show you why in a minute. So here if we have a load, add, decrement, and then a branch not equal. This is what you'll notice. It's not going to run in 1/2 of a machine cycle. That makes no sense. It means it's going to run in either one machine cycle or two. All right? Now the question is this. Why is it two? It comes down to the pipeline architecture of the machine. Remember, this machine, what happens as you're getting an instruction? You fetch, then what happens? You decode it. As you're decoding, what's happening? You're fetching the next one. But if it doesn't know, if the next one, it doesn't know what's happening here, that's why you pay that branch penalty. because it's not sure. I mean, I may fetch something and it's sitting in the instruction queue, and if based upon this test, it may have to bail out. It's going to go from one place to another on the program counter. Okay, so the instruction sequence may have to get modified. So when it's executed, the CPU starts, it fetches the code from the new memory location. The code in the queue that was fetched previously may have to be discarded based upon I'm either going to go here or I'm going to go here for the next piece of code down there. All right? So you pay that what's called a branching penalty. All right? Now what we look at is, okay, in this, if I load up R16 with the number 100, okay, that's going to take one machine cycle. I have a label here of, again, add, let's say R16 to R17. That add's going to take up one machine cycle. I decrement R16 because I'm going to do this 100 times. So that's one machine cycle. And I'm going to branch on a not equal to again. I'm going to be doing this guy for 100 and then bails out to the next one, and that's only going to be one. So basically what you have here is, again, I'm going to just show you the pipelined architecture you fetch on the first clock cycle. I'm executing this fetched command here, and then I fetch the next one. Execute, fetch, execute, fetch, execute, fetch. The problem is when I hit that branch not equal to, it can go two different ways. Okay? All right. So let's see here. Yeah, so I'll let you. It's just it's a penalty that you pay. Let me show you how you actually calculate this stuff. All right. What I need to know is, all right, I'm going to load something with 50, and then I'm going to just do some no-ops, and then I'm going to decrement that 50, 49, 48, 47, 46, all the way down. So we look at it as, okay, this instruction is only once. This no-op instruction here is done how many times? 50, and it takes one machine cycle. This no-op is once, 50 cycles, 50 times. This one is 50 times. This one here is going to be done 50 times, and I'm going to pay a branch penalty for that. When I'm done with this thing and it bails out, I don't pay the branch penalty, and then it's only one machine cycle. Okay? All right, so here we go. Let's say I have a delay. I'm going to write a subroutine to generate a time delay for me. I'm going to define a count to be 20. When you do a define, this is an assembler directive. It doesn't affect the machine. All I'm doing is I'm setting a number equal to 20. So there is no instruction cycle for that thing. Okay? Instruction cycles. I'm going to have a loop. I'm going to have a label here of delay, and I'm going to have another label of again. I'm going to be having loop inside of a loop here. All right? So here's what happens. We've got a, let's see, we've got delay. I'm going to load the delay. Oh, I'm sorry. I'm only doing one loop here. I'll show you how to do multiple loops. Sorry. Here we load this count of 255. Basically goes into count. That number, 255, is going to go into R20. Okay? Because count is defined as being register R20. Up here, I have my label back again, which is basically a no-op, one instruction cycle, no-op again, one instruction cycle, decrement, one instruction cycle, and now I have my branch not equal, which is going to be 2. It's going to be doing this how many times? 255 times. 256 times, actually. I'm sorry, FF is 255. So we have a time delay. Let's look at the inner loop. Inside the loop, we have 1, 2, 3. That's this one, this one, this one. The 2 is in here, and we multiply that 255 times. Okay, so that's how many times. That's what I'm paying for there. All right, now, when I add the 1 here, which is for this. All right, and then the return, since this is a subroutine, the return takes 4 instruction cycles, if you look it up. Okay, that's where we have the 4 down here. So basically, I have this takes care of my loop. This takes care of what's outside my loop. What's outside my loop, I multiply it by 1/10 of a microsecond because my machine's running at 10 megahertz. It's just 1 over 10 megahertz. Yeah. Got a couple of hands up.
Why do you not add an extra one? So when the branch is not equal to is, like when it bails out, does it not include that extra flux head?
Ooh, should I add it a 1? Should add it a 1. Yeah, very good. Let me change that. Thank you. Yeah, there should be another one. Oh, no. Time. If you look on my slide here, I thought about this. There it is. So I added it in, and then I take it off. Yeah. So in reality, then this guy is just, we take the one machine cycle here off. Okay? Same thing? Okay. All right, time delay. All right, you know what? Let me just get to, again, this was just another example here. Here I have a loop inside of a loop. All right? So, all right, so we're going to do this outer loop 20 times. The inner loop gets done 50 times, okay? So here I come in, I'm loading up a register, one machine cycle. I load this register with 50. However, this guy, this L1 is my outer loop, and then I have an inner loop that's going on. So I have this guy's going to set up the outer, and here I'm setting up the inner. So this guy here will get done 20 times because of that, all right? So then I'm going to have inside of here, this no-op is going to be done 20 times 50. Same with the next one, 2050, 2050, 2050, 2020 for these last two here. All right? So we're just setting up the math for it. All right? So in this case I have, all right, 1 microsecond, find the delay. Wait a minute, I think I have. All right, here we go. I'm running, here's what I want you to do. Take this stuff, calculate. Is this code running 25.5? Does it run in 55.125? 50.150 milliseconds? Or 47.3? You need to sit down and do some calculations. And let's see how we got it here. I'll bring it back up for you here. All right, so this is going to be done once, one instruction cycle. How many times is the back going to be done? How many? How many times will this be done? Not 250. It's inside of here. 200. So this will be executed 200 times. All right? How about here? 200 times 250. Here. 200 times 250. 200 times 250. Branch not equal to, all right, this one here. How many will this be executed? The decrement R20? 200. 200. Branch not equal to back? 200. And then one for falling out. All right. Let's get some numbers. What do you think, Miles? What's what? You ready? Let me know when you're all ready. Let's see what we got here. As Mr. Rogers once said, it's a beautiful day in the neighborhood. Won't you be my friend? All right, what you got here, Tony?
Still.
Still? All right, take your time. I kind of plowed through this, I know, but I wanted to, now we can sit back, inhale, take a deep breath, be one with the machine, all right? The best thing to do is to take each line of code and write down how many times. Okay, this is only going to be done once. This will be done how many times? 200. I just... Michelle, oui, oui. You've had it, huh? No mas? No, that's Mexican. It's Spanish. Parlez-vous François? No? All right, not that fluent? All right. How about my South American brothers? Fire con Dios! Right? All right? Fire con Dios. Mota? No mota. No mota. Not good. Yeah, let me get one. Oh, whoops. All right, so we got A, B, C, D. You should be all right there. How many responses do we get? We only got 7. Come on, there's like 32 of you in here. Yeah. We should do a Family Feud here. Survey says! Or Jeopardy. We'll make a game out of this somehow. Antone, what's your guess here? Or calculation, I should say, not guess. Got A? Anyway, you're in the running. How many we have for A? %. Come on, only 14 of you are done. Ah, somebody bailed out of B. Weenie. A's catching up. D's in the running. 15. Come on, only half of you. Yeah. Sure. Where are you going, Miles? Which one? Going with A? Huh? Oh, the next one. Sorry. Huh? I'm not going to show you the answer yet. 16. Looks like seasonal lead here. All right, let's bail out. We got 4 minutes left. Survey says C. Yes! But you're going to that's going to take a 50.150. When I call that routine on a 4 megahertz machine, it will delay for 50.15 milliseconds. Okay? It'll delay for 50.15. All right, let's see, where did I, all right. I'll let you, I'll pop this up here. All right, now we get to the stack. All right. In hardware, the stack pointer sits right here, and notice it's tied into SRAM. The last of the special function registers, the last one is the SREG, which is a status register. The one right before that is going to be the stack pointer high and low. They're going to be the last two in there before I get to the status register. But in hardware, that's where it sits. Okay? You will notice that it is inside this little thing next to the program counter. The stack pointer is tied in with the program counter. The reason is this. When I call a subroutine, what happens to the program counter? Where does it go? To the physical address of where the subroutine or function starts. It's going to chug along in that subroutine until it hits an RET, and when it returns, where does it return to? Where does it return to? I call, it jumps down, the program counter jumps down to where it is. It's almost like a jump. It goes through that code, hits an RET, and where does it come back to? Call, other code, subroutine. Where does it come back to? It comes back, does it come back to the call statement? It comes back to the next instruction after the call. The question is, how does it know where that is? As soon as I do a call, the physical address of the next line of instruction gets put onto the stack. And when the return happens, it pops off to the stack back to where? The program counter. That's it. That's all we're using the stack for. As a matter of fact, you used to use the stack for, the Raspberry Pi has a wonderful stack. Really. If you look at the PIC controllers, their stack is only for subroutines. The PIC 16 series, you can only call up to 8 subroutines because that's the length of that stack. It's a very small stack. Our stack is physically going to be SRAM all the way down at the bottom, and it's going to work its way up. So you can call as many subroutines as you want, just as long as you don't start overlapping things in there. All right. Oops. And we're almost. All right. So basically, the idea is we're going to be looking at a 16-bit, all right, stack pointer. Now again, this stack pointer is in SRAM, but it's holding the address of where I'm going to be going over in Flash. All right? So, and again, it's 16 bits, but we can extend this out to 22 if we need to. All right? Right now, we're only going to be worried with 16 bits. See you Wednesday. I posted up homework for Chapter 3. The quiz. We'll catch up with you on that.